Two of the most precise measurements in modern cosmology disagree about something basic: how fast the universe is expanding right now. One method says roughly 67 kilometers per second per megaparsec. Another says roughly 73. That may sound tiny, but in cosmology it is big enough to be a problem. And the unsettling part is this: as the measurements improved, the gap did not simply disappear. This is called the Hubble tension. It is not proof that our picture of the universe is broken, but it is one of the clearest places where our best cosmic model and our best local measurements do not line up. If the mismatch is real, it could point to missing physics. If it is not, it could reveal a hidden flaw in how we measure the universe. First, the fact everyone agrees on: space is expanding. Distant galaxies are on average moving away from us, and the farther away they are, the faster they appear to recede. The number that describes this relationship is the Hubble constant. Despite the name, it is really the current expansion rate of the universe. The trouble starts because there is more than one way to measure it. The first major route looks at the early universe. Satellites such as Planck measured the cosmic microwave background, the oldest light we can see, released about 380,000 years after the Big Bang. That light contains a pattern: tiny temperature differences across the sky. Using the standard cosmological model, scientists infer what the universe was made of, how it evolved, and what today's expansion rate should be. That answer is about 67.4. This is not a direct stopwatch measurement of expansion today. It is a prediction from early universe data, interpreted through a model called lambda cold dark matter, or lambda CDM. That model has been extremely successful. It explains the cosmic microwave background, large-scale structure, and many other observations. So when it gives a number, cosmologists take it seriously. The second major route starts nearby and builds outward. This is the distance ladder. Astronomers measure distances to stars called Cepheid variables, whose pulsing brightness reveals how far away they are. Cepheids calibrate supernovae of type Ya, explosions bright enough to be seen across vast cosmic distances. Then those supernovae are compared with the redshifts of their host galaxies. This gives a more direct estimate of the current expansion rate. The SHOES team has reported values around 73. Here is the tension. These methods are measuring the same universe, but they give answers separated by much more than their quoted uncertainties. Depending on the exact datasets and analyses, the disagreement has reached around 5 sigma, a statistical level that in particle physics would be treated as very serious. But cosmology is not a clean laboratory experiment. Hidden systematic errors can survive for years, so the first suspect is measurement error. Could Cepheids be misleading us? Maybe dust dims them in complicated ways. Maybe stars crowd together in distant galaxies, making them look brighter than they are. Maybe metallicity, the chemical composition of stars, affects the calibration. These are real concerns, and teams have spent years testing them. Then the James Webb Space Telescope entered the story. JWST can see Cepheids in infrared light, with sharper resolution than Hubble, in many crowded regions. Early JWST checks have generally supported the Cepheid-based distance scale, rather than eliminating the tension. That does not close the case, but it weakens one simple explanation, that Hubble's Space Telescope crowding alone caused the entire mismatch. Other distance indicators complicate the picture. The tip of the red giant branch method uses a different kind of star as a standard candle. Some studies using it have found values between the Planck result and the Cepheid supernova result, sometimes closer to one side, sometimes the other, depending on calibration. Strong lensing time delays, where multiple images of a quasar arrive at different times, have also produced expansion estimates, with their own modeling challenges. Then there are baryon acoustic oscillations, patterns in galaxy clustering left by sound waves in the early universe. Combined with supernova data, they tend to agree well with the standard model and the lower expansion rate, especially when anchored to early universe physics. So, the universe is not giving us one clean rebellion. It is giving us a web of evidence, some pointing low, some high, and some dependent on assumptions. If the local distance ladder is right, and the early universe inference is also measured correctly, then the model connecting early times to today may be missing something. One idea is early dark energy, a temporary extra energy component before the cosmic microwave background formed, which would change the inferred expansion history. Another idea involves new kinds of particles, altered neutrino behavior, or changes in dark matter physics, but every proposed fix faces a hard test. It cannot just move one number. It must also preserve the precise pattern in the microwave background, the distribution of galaxies, gravitational lensing measurements, the abundances of light elements, and supernova observations. Many ideas can reduce the tension in one place while creating new disagreements somewhere else. There's also a more philosophical trap. The phrase Hubble tension can make it sound as if the universe has issued a direct contradiction. More carefully, we have a conflict between measurements and inferences. The early universe value depends on the standard model. The local value depends on a chain of calibration steps. Both are evidence-based. Both have possible weak points. Neither should be dismissed casually. What would settle it? More independent routes. Gravitational waves from merging neutron stars can act as standard sirens. If astronomers know the wave signal and identify the host galaxy, they can estimate cosmic expansion without the traditional distance ladder. So far, there are too few events for a decisive answer, but future detections could become powerful. Next-generation surveys from missions such as Euclid, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope will map galaxies, supernovae, weak lensing, and cosmic structure with enormous datasets. They may reveal a subtle systematic error, or they may sharpen the disagreement until new physics becomes harder to avoid. The payoff is not that cosmologists have found the final answer. The payoff is that the Hubble tension is unusually productive. It forces every method to become more transparent, every uncertainty to be hunted down, and every proposed theory to survive contact with multiple kinds of evidence. If you want more short documentaries that separate what we know from what is still disputed, subscribe to Strange Science Files. We follow the evidence first, especially when the universe refuses to give a simple answer. For now, the expansion of the universe remains one of science's strangest measurement conflicts. The cosmos is not necessarily broken, but somewhere between ancient light and nearby exploding stars, something still does not add up.